Hey there. So there were a lot of requests for worked examples for the energy conservation part of this class, so I thought I'd just go through a few worked examples that I have. I'll go through these in lecture as well, so you can ask me questions, but this will be here for reference so you can see how to think about these problems, how to tell when mechanical energy is conserved, how to use that in your problem, and how to calculate various quantities. So to get started, let's talk about this problem. So I'd like you to just pause the video for a little bit and just read the problem on your own time. Okay, I've assumed you've paused the video now and read the problem, so let's get started. If you have these two blocks connected by a light string, then in this case, the only thing doing work on these blocks is gravity. Therefore, we can use the gravitational potential and kinetic energy. Let's write this down in a couple of steps, and each step is going to have a particular assumption built into it, so you can see where these come into the problem. Okay, now I've got my iPad out, and I can start working on this problem. So the first thing that we're going to do is we're going to write down that the change in the mechanical energy of the system is due to the amount of external work done on the system plus the amount of work done by non-conservative forces. Okay, in this particular case, because only gravity does work on the blocks, therefore all the work done is by conservative forces. Therefore we can write down that the change in the mechanical energy is zero. Okay? This is one built-in assumption. If you can use this assumption, you can write down the next equation, which is that delta K, the change in kinetic energy, plus delta U is equal to 0. Therefore, delta K is equal to minus delta U. Okay? So this is where we're going to start. Okay? Now we need to write down delta U. So delta U, so first of all, you've probably seen the gravitational potential is something like mgh, right? What we're interested in is the change in the gravitational potential. So delta U is equal to mg delta h. In this case, we have two masses to deal with. Therefore, we have to add the change in the gravitational potential. So this is going to be delta U is equal to m1 g delta h1 plus m2 g delta h2. In this problem, you can see that if this mass goes down, this mass is going to come up by an equal amount because the tension in the rope is the same. This is something that's built into this problem, and I'm going to go over it in more detail in class. For now, let's move on. Therefore, delta H1 is equal to minus delta H2. Therefore, delta U is equal to M1 G delta H1 minus M2 G delta H1. All I've done is plug this equation into this equation. Let's move on. Therefore, delta U is equal to M1 minus M2 G delta H1. Okay, so that's the first part. Now we can calculate how much the change in potential energy is for the system. But I'm going to do something a little bit better. I'm going to solve basically the speed for these blocks at any point in the system. And I'm going to show you how to do that. So now we have the change in kinetic energy. This is 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Again, because the blocks move together, if one falls and the other rises, v1 equals minus v2, which means that v1 squared equals v2 squared. So there's really only one speed in this problem because these blocks move at the same speed, not velocity, speed. Therefore, we can write the change in kinetic energy as 1/2 m1 plus m2 v1 squared, right? All I've done is I've factored m1 and m2 together because v1 and v2 are now the same. So the 1/2 is the same and the v1 is the same. Now, note that delta U is equal to minus delta K. Therefore, m1 g delta H1 is equal to 1/2. M1 minus M2 G delta H1 equals 1/2 M1 plus M2 V1 squared. Note, in this particular problem, if I go back to the situation that I have, delta H is negative, right? The height of M1 is dropping. Delta H is less than 0. This is important because the initial velocity of these is 0, which I didn't quite put in here. Minus, so this is V final. So the initial velocity is 0, and that's why I can write down the change in kinetic energy that way. Therefore, I can now solve for V1. V1 squared is equal to, dividing both sides by 1/2 M1 plus M2, M1 minus M2 G delta H over 1/2 M1 plus M2. I'm going to rearrange this in a little bit and make this look something like what you might like. Then we can take the square root of both sides. So I finally arrive that the velocity, the speed of both blocks is m1 minus m2 over m1 plus m2 square root times the square root of 2g delta h. Why have I written it this way? I've written it this way because you should recognize this as the final velocity of an object that's fallen from some height, right? Why does this matter? Because this allows us to do one of my favorite things in physics, which is limiting cases, right? Limiting cases help you check whether you've made a mistake in your answer. So limiting case number 1, m1 equals m2. In this case, if we go back and look at this situation, right, if this mass and this mass have the same weight, then and the same mass, then they will balance each other and nothing should move. If we go back to our equation, we can see that if I plug m1 equals m2, m1 minus m2 is 0, and so this whole speed, the speed at all times is 0. That makes sense. Okay? Our next situation is m2 equals 0. If we go back to our slide here, if this mass is 0, that means that this block just falls as a free body, right? And so we should get the velocity of a free body that's fallen from rest with some height h, which you remember from the kinematics unit, which is this. I want to note, this did not involve drawing a free body diagram. This did not involve any assumptions whatsoever other than that these blocks, if one goes down, the other goes up, and they move at the same speed. So for example, if there was a spring in here, or if the tension was not the same, then you would have to deal with that in the problem. But because all of the work in this system is done by mechanical energy, we can solve this problem. I want to move on to the next part of the problem, which is to find the speed of each block when m1 has fallen a distance of 2 meters. Okay? So you'll notice that all I have to do now is go back to my previous equation and plug in 2 meters, right? So the velocity is equal to m1 minus m2 over m1 plus m2 over square root square root of 2g times 2 meters. Okay? So this whole thing is approximately 40 meters squared per second squared, right? For g is approximately 10 meters per second squared. So let's review and just quickly go over what assumptions we made in this problem and how they allowed us to get the equations that we did. Because this is really what I want you to understand about energy conservation. It's extremely powerful, and the trick to a lot of these problems is not going through the algebra. The trick to a lot of these problems is understanding what assumptions you can put in where. So if I go back, the first assumption that I used here was here, okay? So if there were non-conservative forces, for example, if someone was pushing on the block, or if there was friction, for example, maybe one of these blocks was sliding against a wall, then what we could do is we could calculate the amount of non-conservative force work that was done and relate that to the initial potential plus kinetic energy and the final potential plus kinetic energy. The second step that we did, and so there wasn't any, and so that also allowed us to set delta k equals minus delta u. The next thing is we have to find the appropriate potentials. So this is the appropriate potential for gravitational potential. Afterwards, we put in this assumption, which is that the blocks move together, and this assumption here, which is that the initial kinetic energy is 0. Okay, that's built in because I didn't subtract any initial kinetic energy. So I'll go through worked examples where the initial kinetic energy is non-zero. This is a relatively straightforward problem, in part because the initial potential energy, the change in potential energy, is equal to the final kinetic energy because the initial kinetic energy is 0. So when everything starts at rest, you can write down the change in kinetic energy this way. Otherwise, if the system is not at rest in the reference frame that you're looking at, then what you have is the change in kinetic energy is the sum over all the masses I So essentially, it's 1/2 m delta v squared. I say that's a little bit of a complicated statement, so it's this thing. It's the sum of all the masses times the change in the square of the velocities. Okay. This is always true, by the way. This is always the change in kinetic energy. Typically, the trick with energy problems is figuring out whether there's non-conservative forces being worked on and how to get the change in the potential if all of the forces are conservative, and therefore I can use potential energy. Okay, now I want to go over an example of a problem that involves non-conservative forces. So take a minute to read this slide and ask yourself if you can solve the problem, and pause the video, read the slide, see how far you can get, and then when you come back, I'm going to work through the problem. Okay, we're back. So here's the problem, right? We're asked to find the kinetic energy of the box before it encounters the rough patch and the kinetic energy of the box after it passes the rough patch. So remember that what we can do is we can say that the change in kinetic energy is equal to the total work. So for part A, right, we have 1 kilogram and an initial speed of 3 meters per second. So the initial kinetic energy is 1/2 m1 v1 squared, which is 1/2 times 1 kilogram times 3 meters per second squared. Okay, so this is 9/2 joules, right? 9 meters per second times that is equal to 4.5 joules. Okay, Then we encounter a rough patch that's 2 meters wide with a kinetic friction of 2. Okay? So remember, now the total work done by the kinetic friction is the integral of the force over the distance. In this particular case, the kinetic friction force is constant, right? So this is just going to be F delta x, okay? We know delta x is 2 meters. What's F? Remember the formula for kinetic friction is the kinetic friction times the amplitude of the normal force, right, in the negative direction. So the force is 0.2. In this case, the normal force is just minus the weight of the block. So this is going to be 0.2 times mg. In this case, I'm going to use g equals 10 just so I can do this all in my head. A 1 kilogram block with a kinetic friction of 0.2, right? So this is just 0.2 times 10, so that's 2 newtons. Okay, and then, so the work done is 2 newtons times 2 meters is 4 joules. Okay, so now we can calculate the final kinetic energy. Should point out actually the work done is minus 4 joules. So this negative sign matters because the change in kinetic energy is equal to the work done. The initial kinetic energy we calculated, right? It's up here, it's 4.5 joules. So the final kinetic energy, K final, is equal to K final minus K initial is equal to work. So K final minus 4.5 joules is equal to minus 4 joules. K final is equal to 0.5 joules. Okay, so the block slows down. And now, if we want, we can now say, okay, this is 1/2 mv squared, right? And we can calculate the final speed before this thing hits the spring. Now, let's go to the second part of the problem. Okay, so we get this. For the second part, I want to talk about how far is the spring compressed when the mass momentarily comes to rest. And after rebounding, can the box pass through the rough patch again? Where does it come to rest? Okay, so to solve these problems, what we need to do is we need to think about, I have this block and a spring, and now I can think about starting a new problem essentially, where I've passed the rough patch, right? And I have 1/2 of a joule of kinetic energy. The spring constant, K, of this spring is 100 newtons per meter. Okay? So the way to think about this is when the box comes to rest, the final kinetic energy is 0. Therefore, all of our kinetic energy will be converted into potential energy. And once I pass this rough patch, the change in mechanical energy is 0. So again, minus delta K is equal to delta U, right? In order for the box to come to rest, all the kinetic energy is potential energy, therefore minus delta K is equal to 0.5 joules. Okay, finally, we can answer the question, after rebounding, can the box pass through the rough patch again? So now we have a situation in which the box is going this way. We have a rough patch of 0.2 meters wide. And we know from previous experience, remember the weight is the same. So the kinetic friction coefficient is the same. So the work done is going to be the same. But now I only have half a joule of kinetic energy. And this friction is going to do at least, if I pass through the whole thing, at least 4 joules of work, right? But kinetic energy can only be positive, it can't be negative. So we can only do a half a joule of work on this box before it comes to rest. So the answer is no, right? We need about 3.92 to 4 joules, depending on whether you use G as 9.8 or 10, which is more than the kinetic energy of the box. So the box will come to rest somewhere inside the patch. So where does the box come to rest inside the patch? So what we can do is we can say, okay, now the change in kinetic energy is equal to the work done by non-conservative forces, right? Because the change in potential energy is 0. Okay, so the change in kinetic energy when this box comes to rest is going to be, this is going to be 0.5 joules, because remember that spring converted all the energy into potential energy of the spring, and then when it re-expanded, the box flies out on the other side and has exactly as much kinetic energy as when it came in, because kinetic energy was conserved. So in order for this to be true, then what we need is this to be equal to the coefficient of kinetic friction times the mass of the box times g. So this is the force. This is the friction force that's doing work, times delta x. This is the distance the box will travel. Therefore, we get 0.5 over the kinetic friction coefficient is 0.2, 1 kilogram, and g is 10, which is equal to 0.3 meters, approximately. Sorry, I'm doing all this math in my head. 0.25, I should be able to see that. Okay.